Hello everyone and welcome back to Math 127 Pre-Calculus 2. So in our previous lesson, we have learned how to represent vectors, perform operations with them, and then write vectors in terms of their components. So today, we are going to build on those ideas by introducing another important vector operations, which is what we call dot product. So unlike vector addition or subtraction, the dot product produces a scalar or a single real number instead of another vector. Okay, so this operation will help us determine the angle between vectors and identify when two vectors are perpendicular or what we call orthogonal. Okay, so let's go ahead and start. So by the end of the lesson, you should be able to find the dot product of two vectors and then find the angle between two vectors, and lastly, use the dot product to determine if two vectors are orthogonal. Okay, all right, now let's go ahead and begin with the definition. Okay, so we have here, suppose that the vector v is equal to a1i plus b1j, and vector w is equal to a2i plus b2j. So in this case, the dot product is found by just multiplying their corresponding components. So in this case, for example, the a component plus, okay, multiplying the b component. Okay, so or the horizontal and then vertical component. Again, notice that unlike vector addition, the answer is not another vector. So the result is simply, again, a real number. So let's go ahead and work through some of these examples. Okay, so let's just say given here is the vector v, which is 7i minus 4j. Vector w is 2y minus j. So in order for us to solve this, okay, so I'm just going to go ahead and identify the horizontal vector. You multiply that and then add with the product of the vertical components. Okay, so now we have here vector v times the vector w is equal to, we have 7 times the 2. And then again, we will just be adding that to the product of the vertical component. So we'll have here 4, negative 4, and then the negative 1, okay, for the vector w. So now we have here, we have 14 plus 4. So now this gives us equal to 18, okay? All right, so now we have here vector v times the vector w. Okay, so again, if you were able to get the process here, you can go ahead and pause the video and then work on to the two remaining statement. Okay, so now let me go ahead and work on with w times the v, or the vector w times the vector v is equal to, we have here w is 2. Again, and then v is 7 for the a component, and then plus, again, w is negative 1 times the v component, which is negative 4. So now this gives us 14 plus 4 is equal to 18. Now, as you can see, we do have here two of the statements that if you will notice that I do have here multiplying the vector v and then followed by the vector w here, we switch the order of the two vectors. And then we are ending up with exactly the same output. So what it means here is that one of the properties of the dot product is that we do have the commutative property, meaning to say however you write them in order, it does not affect the final result. Okay, all right, now moving on to letter C, we have vector w times vector w. So we have vector w times the vector w, which is equal to vector w, we have here 2, and then another horizontal component for vector w plus the -1 and then another vertical component, which is again the -1. So now we have here 4 plus 1, which gives you a 5. So this is now vector W times the vector W. Okay, so now we have here equal to 5. Okay, also what you are noticing here, that if you are multiplying the same exact vector, this is like getting the magnitude of the vector. Okay, so you remember the magnitude of the vector, and then you square that, and then that's gonna be the multiplying the vector by itself. What do I mean with the dimensions or the magnitude of the vector W? If you remember, if we are getting the magnitude of a certain vector, we just simply get the square root of both of those two components. In this case, we have here the square root of 2 plus the -1 squared. So that's going to be equal to 4 plus 1, which gives you a radical 5. And then like I mentioned, all you need to do is to get the square of this given, what do you call this, of this given measure, okay, which is again the magnitude of vector W. So if that's the case, then therefore the square of the square root of 5 is equal to, just simplified, and as you can see, it has exactly the same output whenever we are multiplying the vector by itself, or simply get the square of its magnitude. Okay, now you have now some ideas of those, some of the properties that we can apply when dealing with dot product with these special cases. Okay, and these are the properties of the dot product. And then I have mentioned the first one. So if you do have vector u times vector v, this is equal with switching those two order, and that would be the vector v and vector u. And then we also have the distributive property. As you can see here, we distributed the u to each of those terms. Okay, that would be also applicable for the vectors. And then we also have the zero identity property, that if you're going to multiply it with a zero identity, and then that gives you a 0. Not the identity property, but the 0. Okay, so in this case now, like I've mentioned, that if you are going to multiply a vector with exactly the same vector, then it's like you are solving the square of its magnitude. Okay, now similar to this with the associative property. Okay, all right, now moving on to associative property, meaning to say that you are creating a different groups here from the word itself, associative. You do have with different associates. Okay, now moving on to the next concept. Okay. All right, so now let's take a look at another way to complete the dot product. So instead of using vector components, we can also use the magnitudes of the vectors and angles between them. Okay, so for example, if we have this vector v times the vector w, this is just the same thing as the magnitude of vector v and then the magnitude of vector w cosine the given angle. So this formula becomes extremely useful whenever we are asked to find the angle between two vectors. Okay, this is useful when we want to find that angle between those two vectors. Okay, now let's reverse that formula from the previous formula. Okay, so if we are given two vectors and need to find the angle between them, we can use this formula. Okay, again, this formula came from here. We just isolated the cosine theta, and so you have here the cosine theta is equal to the dot product between vector v and w, and then the product of the two magnitude from vector v and then w. Then of course, to find the angle, you just need to apply the inverse of cosine. So after computing the fraction, we'll use again the inverse of cosine function to approximate using your calculator, determine the angle. So Now, let me go back with one common mistake is actually forgetting the parentheses when entering the fraction into the calculator. Be sure to determine, sorry, to make sure that the entire quotient is inside the inverse of cosine function, okay? So let's go ahead and practice using the example here. Okay, so find the angle between two vectors v and vector w, and then round our answer to the nearest 10th degree. Okay, all right, so the first thing that we can do, so we know that this would be our a component and of course the b component there. So I'm just going to go ahead and follow exactly, since we're looking for the angle, so I'll be following this formula. Okay, so now I'll have the angle theta is equal to the inverse cosine, and then we have here the 4, the horizontal component, plus the vertical component, -3, and then +2, all over. Now we'll get the magnitude for each of this vector. We know that the magnitude is the square root of a squared plus b squared. Okay, so I'm just going to go ahead and follow this formula to find the magnitude of each. So now we'll have here 4 squared plus the -3 squared. Okay, let me extend that. Okay, and then now I'll have the 1 squared and then plus the 2 squared, okay, from vector W. Okay, all right, so now let me just go ahead and check if this exists under cosine function. Remember the range that our basis for us to say that the cosine inverse cosine function is existing is that we make sure that this value right here should be within -1 and 1. Okay, let me go ahead and check that first. Okay, so now we have a 4 times 1 and then plus the -3. Let me put a parenthesis just to make sure it won't go. Okay, that's not existing. Okay, and then square root of 4 squared plus the -3 squared. Okay, I'll go out from here and then now I'll do a square root again. So 1 squared plus the 2 squared. Okay, all right, now I do have here a value that is within the range of cosine. So now let me go ahead and continue solving for the inverse cosine. So again, this would now be an approximate value now. So shift cosine. Okay, answer. Okay, so that's gonna be approximately, so since I am going to express my answer to the nearest 10th of a degree, so that's gonna be 100.3. Approximately 100.3. I am on the degree mode, so there you go. Okay, and the final answer here must be in the degree mode. Okay, all right, now let's go ahead and illustrate. See if we have that approximate value, which is 100.3 degrees. Let's apply what we have learned from the previous section. So if I'm going to graph this, okay, so we'll have 1, 2. Okay, so the first vector here, vector v, is 4 and then -3. So 1, 2, 3, 4, 1, 2, 3. So this is the terminal point. Okay, connecting that initial and terminal point. So once again, this is vector v. Okay, now I'm gonna go ahead with vector w. So it's 1 and then +2. So that's gonna be our terminal point. Okay, so as you can see here, you will see now that the angle between these two vectors, it looks like almost, again, well, if you're going to look at it I know that the 90-degree angle is again perpendicular, and as you can see here, it's a little bit more than the 90-degree, which is again it makes sense that this is a 100-degree angle, 0.3-degree angle. Okay, so that's how that's what we are solving. Again, the angle between the two given vectors. Okay, all right, so now let's go ahead and discuss parallel vectors. So two vectors are parallel if the angle between them is a 0 degree, meaning that the point that they point in the same direction. Okay, and then or we do have here a 180-degree, meaning to say that they point in exactly opposite direction. All right, so both situations represent vectors that lie along the same line. Okay, all right, now let's finally introduce one of the most useful application of the dot product, which is the two vectors are called orthogonal, okay, if they are perpendicular. Okay, so that means to say that the angle between them must be a 90-degree angle. So instead of finding the angle every time, there is much easier test if, again, vector. Okay, so if vector v, for example, the dot product between vector v and vector w is equal to 0, then the vectors are said to be orthogonal. Okay, and then we will verify this using the example here. Okay, let's see. Okay, so now are the vectors v equals 2y plus 3j and vector w 6i and minus 4j orthogonal. So there are two things that we need to, there's one thing that we need to check here. First, we need to check whether these two vectors form a right angle. Okay, so in this case, let's go ahead and use, since I want to know the angle between these two measures, then therefore I am going to, okay, apply the inverse cosine. Okay, so this one. Okay, let me go ahead and apply that. So angle theta is equal to inverse cosine. We have the vector v dot product between them over the magnitude of each of these two vectors. Okay, so now we will do the substitution. Okay, so we have here vector v, we have 2 times 6 plus 3 times the negative 4 over, we have here 2 squared, and then we'll have plus 3 squared, and then for vector w we have 6 squared plus a negative 4 squared. Okay, all right, let me just go ahead and check if this exists. Okay, so we have 2 times 6 plus 3 times the negative 4, okay, over that radical 2 squared plus 3 squared going up. Okay, we have 6 squared plus the negative 4 squared. Okay, so we do have here a 0, okay, and again it's between negative 1 and then 1, so that 1 exists. Okay, let me just go ahead and write that. So inverse of cosine of 0. Okay, so that's gonna be now inverse of cosine, answer, which is a 0. Okay, so there you go, we now have here a 90-degree angle. Okay. All right. So what does it mean if it is a 90-degree angle between them? So we do have there a 90-degree angle. So that means to say that since we are getting a 90-degree angle, now we can say that this is indeed an orthogonal. Okay. They are indeed orthogonal. Okay, the two vectors are orthogonal. Okay, there you go. So if you are to visualize this two measures, let me just go there. Those two vectors. Okay, let's say vector v. Okay, so this is vector v. And then vector w. Okay, this is vector w. Okay, so as you can see here, it's obviously, okay, it's visible that we are creating an orthogonal vectors. Okay, since the angle between them is exactly 90 degrees. All right. Okay, so again, so we now have here checkpoint part. Okay, oops. Okay, the checkpoint part. So once again, it's your turn. Okay, so please complete the checkpoint problem. Try to compute the dot product. If you notice from the previous section, I have given you one exercises there that has something to do with the dot product, for you to be, do some advanced reading, of course. And then find the angle between the vectors, determine whether the vectors are parallel, orthogonal, or neither. So again, let's just go ahead and summarize what we went over, okay, for this lesson. I know it's a short lesson. So for today, we have learned what the dot product is, how to compute the dot product using vector components, and then how to use the dot product to find the angle between two vectors, and then finally how to determine whether the two vectors are parallel or orthogonal. Okay, so once again, the dot product is one of the most important operations in vector mathematics, and we will continue to appear. It will continue to appear in the future math, in, for example, physics or engineering, or even in computer science courses. So again, thank you for watching. Please continue practicing the example and of course the checkpoint part and your homework exercises. And once again, I'll see you in the next lesson.